Hi, and welcome to my P99 CONF talk. Today, I'll be talking about an experiment that I did a few years back with the Go runtime, and I'll talk about how it helped me in understanding a few things about the runtime, the GC, and a few other things. But before that, let me give you a brief introduction of myself. I'm Aadhav. I've been working with Go since the last year or two, and I love working with distributed systems, databases, and performance-related things. I also work on some experiments, and you'll be seeing one of those in this talk. So, in this talk, I'll be covering a few things about the experiment, what worked, what didn't, some ongoing work, and a bit about Go runtime observability in the existing ecosystem. But what's the experiment all about? So, back in 2022, I was trying to understand how the Go GC works as someone who was new to the language. And I ended up seeing a visualization of the Go GC tricolor abstraction, and I wanted to build something similar but with real data extracted from the runtime. So I started exploring the runtime to get some ideas, and I started working on a small prototype to see how feasible it was. But let's understand a few things about the GC itself. The Go GC is a simple concurrent tricolor mark and sweep GC where you have two actors uh, called mutators and collectors. Mutators are responsible for allocations and mutations in the heap, whereas collectors try to find and free garbage. And there's two phases in the GC process. Uh, the mark phase tries to identify accessible objects and marks them as active or in use, while the sweep phase tries to find unmarked objects and determines them as garbage. Although this explanation is pretty basic because the Go GC has a few other things like pacing, etc., but I can't cover those due to time constraints. But what does the tricolor abstraction mean? So the GC tries to separate objects into three different color sets, which is the white set, the gray set, and the black set. The black set has objects which have been scanned completely and whose descendants have also been identified, whereas the gray set has the roots discovered but the descendants are not discovered. And the white set are objects where the collector hasn't reached yet, or they may or may not be reachable from the root. And here's a quick visualization of how it works. So A is the root and it starts from the root. It tries to mark all the descendant nodes, and then the F node is the garbage which is collected in the sweep phase. But before that, I also needed to understand what information I needed to extract and how do I extract it. So at a high level, I wanted something which could help me in getting an object graph representation for visualization. And I had three options to choose from, and I'll be revealing the third option later in the slides, but let's start with the first option. The runtime package was my first option as it has a ton of functions related to the Go runtime. One candidate worth checking out was memstats as it's used by a few observability tools and it's something which I've read previously. Memstats is essentially a struct which contains statistics about the runtime, including heap allocations, GC timing, etc. Although memstats is a great place to find statistics related to the runtime, it's still numeric in nature. It could be useful for most tools, but for this experiment, I wanted something which could help us in building an object graph representation. So I jumped on to the next option, which is to utilize existing Go tooling. So after a few days of research, I found a tool in the Xdebug package called ViewCode, which can be useful for observing code dumps for a group process. I was pretty excited to try it out, but it failed at the heap dump parsing stage and had a few panics which I couldn't resolve on a fork version as well. The Go team is recognizing the problem and is planning to solve it in an open proposal, but at that time it didn't work out really well. So I moved on to the third option, which is similar to the second, but in this option, I tried to get a heap dump using the debug.write heap dump function. A heap dump essentially is a sequence of records, and Go writes 17 types of records to the heap dump, including objects, interfaces, which is itabs, and a few other things. And a heap dump is a natural candidate for extracting information about objects as uh, it has information about those, and it could be useful for building the object graph representation. But there were a few other options which I considered. One of them was to fork Go, which is a tempting idea, but I didn't pursue it for a few reasons. The first thing which made me not pursue this option was how fast the runtime works. The runtime moves at a very high velocity, and my patches will require constant fixes or require maintenance. And the second thing is it's challenging to extract information out of the runtime for someone who doesn't have enough experience with the runtime source code. But I personally find the main reason was how I wanted this to work on normal Go installations and not just my fork version. So I didn't pursue this option. But coming back to the implementation, the idea was pretty simple. You just get a heap dump, parse it based on the documented format in the Go wiki page, and use that information to generate an object graph. And I wanted to work on a minimal algorithm that tries to utilize multiple heap dumps and identify transitions and apply the trajectory abstraction based on it. So here's a screenshot from an older version which had the object graph generation and the coloring implementation, but the implementation was pretty basic. And this is from a rewrite where you have an interactive object graph, but I haven't integrated coloring to this yet. So what's left to do? I personally wanted to try GoCore once it's stabilized, but another interesting idea which I'm exploring right now is to use delve as a means to retrieve type information as it could be really beneficial for the visualization. But there's some ongoing work outside of my efforts in the heap analysis space. And the first thing which I wanted to highlight was the open proposal which I mentioned previously, which tries to make Go core and core work at GoTip. And the second one is a pretty interesting tool from ByteDance for heap analysis, which uses delve to retrieve type information. And there's also HeapSparse, which provides a small toolkit to work with Go heap dumps. So I did fail, but I wanted to try and learn about Go runtime observability. So at this point, I had understood most of the Go runtime, and I wanted to explore how much of the Go runtime is observable. But before that, let's try to break down the Go runtime into smaller components. And the first thing to note here is the GMP model, which notes where G are the Go routines, M are the threads, and P are the processors. And then we have things like the scheduler, the garbage collector, the net puller, and some concurrency primitives like channels, etc. Right now, we have a great set of tooling that could help us in observing the runtime, including pprof, execution tracer, GC traces, and a few more tools, which I'll be covering in the later slides. But let's start out with pprof first. Pprof has 5 profiles: a CPU profile, a memory profile, a Go routine profile, a block profile, and a mutex profile. So the CPU profile helps in identifying hotspots in your code which consume a lot of CPU time. And all Go code spending time on CPU is observable here except IO. And the memory profile is helpful in finding places which perform a lot of heap allocations. However, CGO allocations are not observable in this type as per my observation. The Go routine profile is helpful in getting information about Go routines. The only limitation in this profile which I could find is that it doesn't report short-lived Go routines in the profile. The block profile is helpful for understanding time spent by Go routines being blocked on waiting operations like channel operations, mutexes, etc. However, a thing to note here is that in progress blocking events are not observable. IO and sleep are also not observable in this profile type. And there's another profile type which I mentioned previously is the mutex profile, which is helpful for understanding time spent on lock contentions. And the non-observable parts in this profile type are sync wait groups and places where your runtime is waiting for lock spins, etc. But you can go beyond preprof. But should you? In most cases, preprof is sufficient and will provide a clear picture of the entire application. But if it's not sufficient, Go still provides you with a few more tools to observe in more depth. And one of which is the execution tracer, which is an extremely powerful tool for understanding your application's execution. It captures a ton of information like coroutine events, GC events, syscalls, etc. And using the execution tracer is more compelling as the overhead has been reduced in the recent Go releases from 20 to 30% to 1 to 2%. So this is the tracer overhaul issue with the design document and this is the blog post from the Go team. I do recommend checking both of these out if you're interested in knowing more about the overhaul. But coming back to the tracer itself, this is the trace view with the flow events enabled. And there's a ton of information in this view, including timelines, incoming and outgoing flows, and you can drill deep into a particular block as shown here. The execution tracer also provides a few profiles to understand why a Go routine is being blocked to run on a P, which is a logical processor. And you could go beyond that by getting an analysis on a group of Go routines. So, for example, this is how a summary table looks like, where you have Go routines grouped by different types or different functions. Now, if we take this is called read function and click on it, we end up in this screen where you could get a detailed breakdown of each Go routine's execution time, block time, wait time, and clicking on the Go routine ID will open up a trace for further analysis. But if you find that a bit overwhelming, you could get away with GC traces as well. And the best part about traces, they have lesser overhead than the execution tracer, as they are focused on a particular subset of the traces, in this case, the GC. Now, this is how a GC trace looks like. And you have different types of information here about the GC. Here you have GC runs, the time since the program started, number of percentage of time spent in GC, and uh, also the sweep and mark scan and mark times, and assist times, background, idle time, and the most interesting part is the start, end, and live heap size with the heap goal. And you also have information like estimated stack size, global size, and number of processes. And there's another type of traces which you could get, which are the scheduler traces, and you could obtain them in a similar fashion, just like the GC traces. And they are pretty helpful for getting granular information like processor information, thread info, and you could also get information about the global and local run queues. And here's a scheduler trace. Uh, it has uh, the times and star and processor information, the thread information, which also includes spinning threads and required number of spinning threads, and also information about the number of Gs inside the global and local run queues. FGProf is another tool which I wanted to highlight here. It's a sampling Go profiler that can capture both on and off CPU times, which is very useful as the normal profiling tooling provided by Go cannot capture this information. There are a few tiny limitations with FGProf. The first is due to its implementation, as it's implemented as a background Go routine, and any scheduler delays might affect its working. Another limitation is that it scales O of n with the number of Go routines, so it might be slightly less efficient on programs with a higher number of Go routines. But you could go even further. The runtime slash metrics package is a great source to extract metrics about the Go runtime, and there's around 88 metrics exposed as of Go 1.23. However, the Go team is planning to introduce a recommended set of metrics in an open proposal. And the proposal aims to define around 10 recommended metrics for usage. As right now we have these set of metrics, and I've tried to group them based on each runtime component. But I do recommend checking out the documentation for understanding what each metric means, and you could decide which ones make sense for you. But there are a few opportunities that I also wanted to highlight. One of them is utilizing eBPF, as it could be used to instrument areas which aren't exposed or observable by existing Go tooling. So coming to the conclusion. So finally ending up in a rabbit hole wasn't that bad. It helped me learn a lot of things about the Go runtime and the current ecosystem around runtime observability. And as you have seen in the previous slides, Go is enriched with a ton of tooling. I personally find it to be really useful for understanding what's happening underneath, and it wouldn't be possible without the contributors and the Go team who have worked on improving this experience over the years. I recommend checking out the Go documentation and Felix's profiler notes to understand more about profilers. And thanks to Felix for also reviewing the slides for this talk. And that's pretty much it. Thank you for joining my talk. These are my socials, and I'll be putting up a more detailed write up on my blog soon. But thanks for joining once again. I hope you have a great day.